All right, well, let me share my screen here. Hey, Nathan. I've got like my iPad up on the other side with the Discord so I can look over. So if I'm looking over for a minute, that's what I'm doing. Not ignoring you. All right. So let's pick up where we left off. So we are back to our little project implementing actors with ZIO. We did one session on it, and I think there was a good amount of interest in it. So I think we'll probably do a couple of sessions and try to build it into something that we can do something somewhat cool with. I'm thinking maybe be able to have like different processes or potentially even different like machines that are communicating with each other with through these actors. I think that'd be a cool thing to do. But let's start off by just reviewing where we are. So we start off by defining this actor trait here. And so an actor accepts messages of type message. And this message type gets parameterized by the response that the message expects back. So for example, in our little example here, we said that we had this temperature actor that accepted temperature messages. And in particular, you had a set temperature message and a get temperature message. The set temperature expected response of this unit, and the get temperature expected response that was a double. And one of the design decisions we made last time was that we wanted to support both these send and this ask pattern. So the send is basically fire and forget. And I think some magic factors actually say that like essentially all communication should be this way. But the ask pattern is saying, hey, I want this response back. And with ZIO, we can suspend. We're suspend without actually blocking the thread. We asynchronously suspend, but we still suspend until we get the response back. So in a way, this is very nice because we can actually like get a response back, which makes our programming model easier. But it does create the risk that we program in a way that creates bottlenecks. If one of our actors is asking another actor for something, they're then not processing anything else while they're waiting to get a response back to that thing. So that's a little bit of a choice we had. Maybe we could think of refactoring that, and we could have like two subtypes of actors, and like basically like one trait would just give you the send, and then another one would give you the ask. But right now we're just giving you all of it right here. And then to start to flesh this out, we had this example where we created this temperature actor. And I think what we saw here was this was good in a way of we got to just like explore the problem domain, and we ended up implementing a temperature actor that we could do, I think, a very actor-like workflow with, where we said, well, we make an actor and then we send a message to set the temperature, and then we ask it what the temperature is, and it gives us back the temperature, and then we print it out. And so if I just get this going, this is called actors. Yep. Let's run this. Yeah, so we get temperatures 42. So that's great. But I think what we have here is, as is often the case when we do these initial explorations, our code is, I'd say, a little bit of a mess here. And I mean, not in terms of just like the actual operators are a mess, but it's kind of mixing up, like we've got part of this thing, like kind of this here is mostly our business logic, right? Of saying, hey, if you get a set temperature, then set the state and just succeed with a unit value. And if you're asked to get the temperature, then get it back and return it. But even this is kind of mixed up with some stuff about like this, like promises and completing them, and like this ref and getting or setting it. And then we've got all this other stuff. We've got like forking this fiber and forking into the scope and creating a queue and creating the ref. And here, like create these promises and offering them. And so I think the first thing we want to do today, and then we can make a little bit of like an agenda for ourselves. So I think the first thing on our agenda would be split actor definition logic to separate business logic from actor machinery. That's the first thing I definitely like to do today. Then we'll see how far we get. But I think the second thing I'd like to do is implement some version of an actor system. So right now, when we created our actor, we just created our actor ourselves, which is totally fine in this case, but I think doesn't necessarily give us all the behavior we want to. That one, I think typically we have this concept of kind of there's an actor system that has a view into all these actors. And so like when we shut down the actor system, we shut down all the actors. And even more than that, I think eventually, if we want these actors to be distributed, then we can't kind of have people just interacting with the actors themselves because the actor might not even be on our system. So I think the actor system is kind of going to abstract over that and is kind of going to say, if you want to talk to an actor, it's going to eventually give you back the result, but it may do it by just interact directly with an actor if it's local, but it may also communicate with an actor through a remote protocol if the actor is on another machine and then get back the result and give it to you that way. So I think the actor system is going to be an important abstraction to enable that. And I think related to that, I think we could have a goal to implement a concept of, and I'll call it like an actor reference, separate from an actor itself. And so that again would be creating some separation there to prepare us for that distributed case where the actor reference is kind of going to tell the actor system like, okay, I want to talk to this actor, but is going to not necessarily be the actor itself because the actor itself might be running somewhere else. So I think that's, I don't know if we're going to get through all this today, but I think that's kind of going to be our agenda, and we'll just work through that. Definitely jump in as we go through here if you have any questions on any of that, or if you feel like that makes sense or doesn't make sense. Okay, so let's look at splitting out this logic. So I think one way I would think about this is like if this thing kind of had our quote unquote business logic, admittedly with some other stuff going on, we want to think about what's going on here. And essentially, how do we take this thing and take it from being code that we're writing here ourselves to being a parameter that we're taking as an argument? Because if we can do that, then we can essentially turn this from make temperature actor to just make, taking that thing as an argument, and then we can make everything work the way we want it to. So let's explore that a little bit. So I think we're saying I want make, and right now I'll just give myself an empty set of parentheses just because I need to figure out what's going to be in there, not because that's actually right. And I'll even put a question mark here just for a sec so we can kind of explore this. Okay, so let's then think about what this thing is doing. So we're basically saying based on a message, we want to give some type of response. Or basically we're passing that through the promise, but that's a little bit of the machinery. We're taking in a message. We're giving back a response. Here it's like either a unit or a double. And we're also getting the state in some cases. We're getting the state in some cases. And we're also updating the state in some cases. So let's try to put that into kind of a data type. So it sounds like we have something like basically, this is not going to quite compile yet, but let's just kind of write it out and then we can kind of do it. So we could say this is really looks like something from like S message to S of response, right? So we take in some state and a message, and then we potentially change the state and we return some type of response. And maybe we want this to be in a ZIO workflow so that you can do other things in your actor beyond just updating the state, that you could like write something to a file, or you could log something or do something like that. So let's try to get this to the point where it can actually compile a little bit, and then we'll kind of build this out. So I'm going to call these state. Okay. And then I'm going to take in a message. And we've said everywhere else that our messages are actually parameterized on this response type, right? So this will be a message of a response. So we're going to take in a message that expects a certain response, and then we're going to return back that response. Okay. Then I think we said we were interested in this being a ZIO. So let's make that a ZIO. Right now we're saying this can't fail. It has to express any kind of failure through the response, which I think is maybe okay. We could potentially allow this to have some type of environment. Maybe we can do that now. Let me see if I can format this so it's readable. There we go. Now I have to need to fill out what this is. So this needs to return an actor. And the actor is going to be an actor that accepts this message type. And now this is starting to look pretty good. I think there's one thing that's missing here. If I go back to look at what I had here. Does anyone have an idea of what is missing in the signature? Just maybe thinking about it conceptually. Like, again, we're not doing any implementation yet, but just what, if we just look at kind of these types and we think about data, like what's missing here? So think about what we need to actually run this thing. So this is something that's going to take a state and a message and give back a new state and a response. And yeah, one has exactly right. We're missing an initial state. And we can also see that up here. If we kind of focused on this, and this is where most of our business logic is here, but we had kind of one more thing that was specific to us of like here, we started with this 0.0, which is, I guess we started with the temperature being 0 because we needed to have some number to start it with. Maybe we could have made an option of a double or something, but we just made it a double. So that's exactly right. So let's maybe add that in here. Yeah, I think that's right. I think John is finishing the metaprogramming workshop in like 45 minutes, I think, based on schedule. So yeah, maybe we could have changed the time, but sometimes the show has to go on. So I'm sure people who are doing that are having a lovely time and can pick this up on the recording. So yeah, so let's add in the state here. And now I think this looks pretty good of basically every time, like what an actor does, is we can send it messages, and every time we do, it's going to take whatever state it has, or the initial state if it's the first time it's being called. And it's going to take that and the message, and it's just going to apply this function to it. And it's going to return back a new state and a response. And it's going to send the response, at least if it's the ask. If it's the tell one, we won't even bother sending the response. And it's going to update the state. So that's what we got here. And now we can get rid of this thing, which is nice. So let's go ahead And let's now see if we can actually implement some of this. So I think I'm going to start by just copying and pasting my code here. And then I'll try to generalize this a little bit. So basically, maybe I'll call this Q. So we're still going to make a Q. And instead of being temperature messages, it's now going to be this generic message type. Then we're going to make a ref that's going to contain our initial state. And then our actor logic, we're going to take a value from the queue, and it's going to give us a message and the promise. And now, instead of having this, we should be able to replace that with essentially using our function f. So let's try doing that. So I should be able to try, so I can do ref.get. That's going to give me the state. Just to make this question for now. And, oh, this is just S. Okay, oops. Okay, so I've got the state and I've got the message here. So then I could do F of state message. And that's going to give me a new state and a response that I need to do something with. And then I think here I'm just going to have to, let's see. I just need to take advantage of the fact that I know that this is the right type. So I think I can just do message dot as instance of message response. Yes, so let's just start to fill this in. So this is then going to give us a new actor message. And then I'm going to have to implement these two methods. And let's see. Oh, so this is just catching a good mistake I made here. So if this takes environment, then this is also going to need an environment. There we go. Let's format that. I don't really believe that is already formatted. Okay, I'm not sure why that's, maybe that is formatted. Okay, fine. So, oops, let me just get the compilation going again here. Okay, so we've run this function. We've got an updated state and we've got a response. So here then, we would need to set the ref to the new state. And notice that here, we don't need to worry about using an operator like ref.update or ref.modify because we're the only ones who are interacting with this ref. I think this is actually a point that I think Naveed made last time that like, since we're the only ones interacting with this ref, we don't strictly speaking need a ref. This could be something like a var. But I think here, just to kind of keep us in this functional world, I'm going to use ref anyway. So basically, we need to update the state with the new state. And then we need to complete the promise with the response. And I think we're going to need to use another as instance of here to use the fact that we know that these message types match up, even though that's not reflected in this here. So I think we can do promise as instance of promise message response, I believe. Let's see. Promise nothing. Message response. And it's not a message response, it's just a response. Okay. So now we've kind of abstract that logic out. And then this logic here, I think we can basically just take this logic here that was in this temperature actor. So the send is going to make a promise. And then it's just going to offer the promise to the queue, and it's just going to return immediately. And the ask is going to make the promise. It's going to offer it, and then it's going to wait for it and return its result. So now I think we've got a implementation of this make here that essentially encompasses all the functionality we had in this both make temperature actor as well as this definition of the temperature actor, just pushing the kind of business logic into this function. Does this make sense to everyone? All right, awesome. So our test for this is basically, can we now blow up really both the make temperature, or can we re-implement make temperature actor in terms of make and blow away most of the logic here and here? And let's try to do that. Let me do one thing first, which is right now, this is all this example thing. Let me actually make a companion object for the actor. And now that my make method doesn't really know anything about this temperature business, let me pull this up into the companion object of the actor. Okay, so now let's try to get rid of this. And let's try to get rid of this. And now we got implements. So now we could do actor.make. And this is going to take two parameters. So we said the first parameter make is the initial state. And we said before that was this 0.0. And then this thing here needs to be a function that takes the state and the message and with a ZIO returns a state and a response. So let's try doing that. So I think I can just do this with an inline set of case statements. So I can do something like case state temperature message dot set temperature value case state message dot get temperature. Okay, so far so good there. And then let's think about our logic for each of these. So if it's this, each of these, we actually need to return two things, because we need to return a new state and a response. Oh, we need to return a ZIO of this, excuse me. So let me start with just ZIO.succeed, two empty things, and we can do more in a second. All right, so if we're setting the temperature, then we need to, the first one of these is the state. So we need to, in this case, we're just setting it. We're not like updating or incrementing, we're just setting the temperature. So all we need to do is set the state to the value, and we can return the unit value here. And if we're getting the temperature, then we can just leave the state unchanged, and we can also return it. And if we want to, if we feel like this is more readable, decide whether we like it or not, but we can use the little arrow thing instead of having the nested parentheses there. It's just a little stylistic thing. And there we go. So let's now try running our program again. And boom. So we've got the same behavior. And now I think this is like much cleaner, right? We say, here's our initial state, and this almost exactly just expresses our logic. I mean, maybe we could have a variant that doesn't take the ZIO, but I think probably having the ZIO is there is good for like anything we want to do that's like more serious if we want this actor to like write things to a file or do anything like that. So I think we can kind of declare victory on our first objective here, that this now seems like a much nicer way for us to make actors with this actor.make. And now this actor.make basically encompasses everything, all of our like actor machinery logic, right? Of like making this queue, making this ref, using the fork scoped with the fiber, doing all this like casting internally, like all this is just wrapped up here. So as a user, you now just have to do that. Does that make sense to everyone? And does anyone have any questions on this part before we move on here? I'll just give people a minute here. Yeah, it's pretty cool. And I think one of the other neat things about this is it just, I think maybe gives us more insight into even like what an actor is, because this type signature, if you look at it, it should look in a way very similar to some other things that you might have seen. Let me see if I can actually find some of them for you. Let's see. So can I go to, let's see if IntelliJ or VS Code will actually let me. Yeah, I don't want, see, I don't want, I have no idea what this thing is, and I don't want this empty one. I want the actual one from ZIO. But here, let me open ZIO for a sec, and I'll show you this. So one thing you could look at that maybe looks pretty similar to this is this operator here. So this is map a cum on a chunk. And so this basically says, well, I'm going to transform an old chunk into a new chunk by statefully mapping it over it. So I'm going to start with some initial state, and then based on that initial state and each element in the chunk, I'm going to produce a new state and an output, and I'm going to give you all those things as a chunk. So you could think of here as maybe you have a chunk of input messages, right? And we're starting with initial state, and given the chunk of input messages, we're giving a chunk of output messages. So this looks fairly similar. We don't have quite the kind of message parameterized on the response, but we just have the A's and B's. And this is doing it as kind of one whole chunk versus individually. But this is looking very similar. Another thing that we could look at that would be along those lines is there's a similar operator on streams, right? So I think a stream is another thing you could think of as an analogy for this of you were going to have this stream transformation that takes in a initial state, right, and an element of type A, and it's going to produce some output element. And it's going to emit all those output elements as a stream. So yeah, as Juan said, you can think of, I mean, yeah, it is a state machine with a queue in front of it. And you can, once you start to see that, you can see a lot of analogies for it. Right, here's the MapAcune version as a pipeline. So this is maybe an even clearer analogy of this pipeline is going to be defined starting with some initial state, and it's just going to accept in messages, and then based on this function, or here they're called out and out too, but it's going to take out messages, and based on the state in the out message, it's going to produce a new state, and it's going to emit an out to message, and it's just going to keep doing that forever. So there's obviously, you can see there's like a little bit of a difference here of like here, these out to messages are getting emitted downstream in the stream architecture versus in our actors, the out to messages are getting sent back to the original sender. But there's a lot of similarities here. And I think, yeah, starting to abstract over these things a little bit, you can start to see some of the similarities between these different things. All right, let me see if I can get us back to our original thing here. Hold on a sec. Screen share. Okay, there we go. So yeah, whereas we started out where kind of the actor was just this thing and we were figuring it out like a little bit as we go, like now this is giving us this like very well-defined model of, yeah, the actor is basically a state machine that you can send messages to, and each time you send a message to it, it's going to process it using the state machine. Okay. So I think here we can do a check mark next to this. I'm not sure how to do that ASCII check mark, but we'll just note that we have a check mark there. So next thing we're interested in is some version of an actor system. And maybe one way we could think of this is we see here that right now when we create this actor, one of the things it returns is it returns a scoped workflow, which means that the scope is essentially controlling when the actor is going to be shut down. But I think one of the things you typically have with actors is you have this concept like an actor system, and versus every time you make it, you get a scope. It's more like the actor system. When the actor system is shut down, it will shut down all of these actors. So why don't we start to work towards that actor system, and that'll also push us in this direction of being having at least the architecture for doing a more distributed version of this. So I think the first thing I'm going to do here is I'm just going to do a little bit of cleanup. So I'm going to move this example to its own file here. And I think I'll just rename this to the actor. And maybe I'll actually create a package for this. So what if I create a ZIO package, and inside this I'll create an actors package. Obviously there is an actual ZIO actors, but we'll just kind of forget about that for the purpose of this little thing that we're doing here. And so then this can be in actors, and then this I can ZIO actors. Let's make sure that's actually compiling. Great. Okay, that'll just let me keep things a little bit more organized as we create some additional data types here. Okay, so let's think then about this actor system. So what is the defining interface of an actor system? Well, I think we just said, I think maybe the most important thing about it is that it lets us make actors. I think we're kind of looking to go from a world where maybe this method actually no longer exists as a public method, but is just something you do through this actor system. So let's try exploring that. So I think probably the easiest thing we can do is we can just start by taking this make method here. And we'll get rid of this scope here because we'll say that the scope is going to be essentially controlled by the actor system instead of being controlled by when we just make each of these individual actors. So an actor system will give us an ability to make an actor. And then we will need a way to make an actor system. Come to in a second. And we said one of the things we're interested in doing with the actor. Oh, we need to input ZIO here. Okay. And we also said one of the things we're interested in doing with the actor system was being able to shut it down. So let's also make that part of the interface. All right, and let's then start to think about how we could do this. So one of the ways I sometimes like to do this is just a little bit of a stylistic thing, but I like to sometimes just do this in line. And so I'm going to assume I'm going to need some workflows here. So I'm just going to give myself a dummy one right now, just to this for comprehension compiles. And then I'm going to yield a new actor system. And I'm going to have to implement this interface. And let's see what I do here. Oh, and I just need to give these things question marks because I haven't implemented them yet. There we go. All right. So I think probably the make method is going to be the harder method to implement here. And I think that may give us some clues about what it's going to mean to shut this down. So let's start with the make method. And I think probably the easiest way to try to implement this is also the laziest way of basically try to just reuse what we already have here. So an easy thing we could do is we could say what this is we do super lazy. I could just do actor.make SF. Now that doesn't quite work. And we can see why from this error message here. And maybe let me just copy this down here for a sec so we can see this. We lost the highlighting, which is actually nice down here, but basically it's this scope that is the issue. That make here returns a scoped workflow, but we said we don't want to expose a scope here. So a really easy thing we could do is we could say, okay, well, fair enough. That means we need to make a scope ourselves, right? This is essentially going to be the scope of the actor system. And so then the way I can get rid of that requirement is I could do scope.extend. I may need to add a type annotation for the environment here. Let's see in a second. Nope, don't even need that here. So essentially, the scope.extend is like providing that part of the environment. So it's saying this actor did require a scope, and the actor.make required a scope, and the scope we're giving it is the scope that we created right here. And now this is also going to give us a easy answer to what it would mean to shut it down, right? What it would mean to shut down this actor system would just be to close the scope. Now, there's a little bit of a design decision here of like, you could argue maybe we shouldn't actually even expose this shutdown thing. Maybe we should just have this actor system have a scope. And that might be a little bit nicer, because one of the things you gotta watch out for whenever you provide these kind of interfaces that like have this manual shutdown is that you're kind of putting the responsibility on the user to shut it down. So let's see what that looks like. So here, probably the next thing we want to do following up on this is we want to actually make this private to our package, because we want people to create actors exclusively through the actor system. So if we do this, now our little temperature example is not going to compile, but that's okay. So now instead of actor.make, this has now got to be actor system.make. And now we actually need to take an actor system as a parameter, which probably if you've used something like akka and you've had these like implicit actor systems flying around everywhere, this is like starting to look familiar. So now that should be okay, but now obviously this doesn't work. So now I could do something like actor system in actor system.make, and an actor in make temperature actor system. And now my code compiles again. And if I run this, this will work in the same way. But notice that as I've written this code now, I'm actually kind of like leaking here of I've made this actor system, but I've never actually shut it down, right? And this kind of API, I guess what I should do here is at the very end, I should do like actor system.shutdown. But obviously it's easy to forget to do that. Or if like some error gets thrown here, then maybe even if I do that, this code might never get executed. So another way that we could do the same thing is, let's say, instead of the signature being any here, maybe this make should require a scope itself. And then here, instead of making a new scope, I could just do, I could just access the current scope. And then I potentially don't even need this shutdown thing to be in the API at all. So now this goes away. And now this make thing, if my VS Code works, which I guess it may not. Okay, all right, no VS Code right now. But this act.make is requiring a scope, and run is providing an application level scope. So now run is going to make sure this actor system is shut down when my application is done. And of course, any other thing that I do, I can just see from the signature of this that this requires some finalization, and whatever scope I use, it'll be bound to that scope. So there's a little bit of a design decision. I think I may go with this here, but I see Juan is typing, so definitely anyone feel free to jump in, and we can go one way or the other. I'll just give a. So in this case, you here in our implementation here, we do need to extend the scope, because we are saying this thing does not require a scope, and actor.make does require a scope. So we definitely have to provide the scope here, and it's actually very semantically significant that we're doing so, because think about if we do something like, let's go back to our example. let's say I do ZIO.scoped make temperature actor. So this is kind of testing for us, is the life of the temperature actor just bound to this scope in this temperature actor signature, if there is one, or is the scope of the temperature actor bound to the actor system? And the point of bounding to the actor system is this thing doesn't even have a scope in its signature, right? This was my bad. I did not remove that, even though I could have. So this does not even require a scope. And the scope is governed by the life of the actor system. But no, that was a good catch, because this is, I guess, one watch out with ZIO sometimes is it won't warn you if you have more things in the environment than you need. So like, I mean, at least unless your code doesn't compile. So like here, since this was providing a scope, nothing's going to fail to compile if I say I require a scope, even though I don't actually require one. So that's a good watch out there. Okay. So I think we're making pretty good progress here. I mean, this is, again, starting to look more actor-like with the actor system. And I think we've got kind of nice finalization logic here. We've now started to get like a little bit of a nicer just structure here. We've encapsulated some of this. So now the only way you can create the actor is through the actor system. So I think this is getting us in a good direction. I think I'm going to try to explore one more thing before we call it a break here. And that's going to be this concept of, I think we call like an actor ref. And so the idea is essentially, like, I think if you've worked with some of these other things like ACA, like when you like do this like ask or send, you're not actually doing it in a lot of cases to the actor yourself. You're doing it to the actor ref. And essentially the actor ref you could think of as like a reference to the actor, but not the actor itself, because the actor is, maybe not even in this place. So there are a couple of ways we can model this. I mean, at least right now, I think the actor ref and the actor are going to have the very similar, maybe identical interfaces. So we could potentially treat them all as actors, but I kind of like the idea, at least for our explorations here, of kind of having a different type to identify a reference to an actor versus a kind of running actor, especially as we kind of think about the distributed mode. So let's create another data type for that. And so I think an actor ref is going to have basically the same interface as an actor, because the idea is going to be, if you have a reference to an actor, you're going to be able to send them messages and ask them for responses to messages. Maybe eventually this, since it's the running actor, is going to have some other things that are more like a private API, of it's going to have a way to like kill an actor or things like that, that maybe you don't want anyone who just has a reference to the actor to have. But I think these are like the very basic functionalities that we would want to be part of the actor ref API as well. So I'm just going to grab these and paste them here. Yeah, we're going to need to import ZIO, so this will make sense. And let's see. Oh, and this is going to need to be parameterized on the same thing here. Okay. And then I think what we're going to say is that a actor system, instead of returning an actor itself, it's just going to return you a reference to that actor. And again, we may play with this more over time, but let's play with that, with what that looks like. So that means that this thing is going to be an actor ref. And that also means that this thing is going to be an actor ref. And that means that this thing is not going to compile, because this is an actor versus actor ref. And then that also means this thing is going to be an actor ref, which is fine. So that actually leaves most of our code unchanged. Basically, just we need to fix this implementation here. And so I think, okay, I have a silly question. Can we just stuff an actor into a ref? So I don't think that's quite what we want to do, because we want to be able to eventually get to the point where the actor could be on a system on another machine. So I think that the actor ref, at least underlying backing it, needs to be more like some concept of an address, at least in our little system. Maybe not an actual address, but basically something we can use to look the actor up. Because I think initially it might just be, I think we'll probably just initially implement this basically just having a map of all these like little actor refs, but eventually we might have to kind of imagine like we have a server that's backing this, and like when we have this, we like look locally, and if we don't have it, then we call the server and it tells us where it is, and maybe then it calls the other version of it. So I think what we potentially want here is something more like, what if we had something like actors? And maybe this is a map from actor refs maybe we can actually make this even simpler. We can hide some of this internally. I think maybe we can just make this a map from longs to actors. Now, this definitely won't this scale to when we have a distributed version, but we'll kind of hide all of that logic inside this implementation of the actor system. So we'll be able to change that as we evolve without changing the API here. So I think we, let's just play with this. So let's say we also had another, call it a counter here. And so the idea here would be basically this map, these counters are just going to be like the IDs for each actor. So like first time we make an actor, it'll just have an ID of 0, next time it'll be 1, and so on. It'll be kind of like IDs for fibers. And this map is going to be a map from each of those IDs to the actual actor that implements it. So then if we wanted to make one of these actors here, I think we could still do a lot of what we've done before, but let's just try this. Just grab those abstract methods of the actor. And so then these can be implemented by just delegating to the real actor. Okay, so when we make a actor now, we're going to create the actual actor. And we're going to create this actor ref that's kind of a proxy that basically lets you send or ask those messages to the underlying actor. And then we're also going to get an update here. And then we'll just put that inside this map. We're not really doing a whole lot with the map yet. Right now, we're just kind of using this. I mean, this actor ref is just kind of a proxy that's sitting in front of the actual actor. But what it's doing now is you can see that now in terms of the public API, kind of the way you interact with these actors is through one of these actor refs versus through an actor directly. So that'll kind of give us the ability to try to move to more of a distributed model with this without really changing the API here. And you can see that here of now it's just instead of an actor, it's an actor ref, and otherwise this logic is essentially unchanged. And if I run this thing, it works exactly the same way. So I think we're about at time here. And I mean, I think we kind of went through our agenda here of we implemented at least a very simple actor system. And we have a very simple version of supervision of kind of when you shut down the actor system, shut down all the actors. We implemented this constant actor reference. So I think this was definitely good progress. I think some future directions we could think about. One thing we haven't really done yet is our definition of an actor probably needs to be supplemented with at least potentially with some concept of context. Basically, if we want an actor to be able to send back a message, right now it can just send back this particular response, but we could imagine we might want to have something like a context here that has things like the sender or maybe who you are or things like that. If you want to access some contextual information about this actor or kind of this particular message you're processing, that's something we could explore at some point. But I think the other big thing is kind of starting to look at how we maybe move to a more distributed model here. And probably I think maybe the simplest way to think about that is kind of basically getting this not all being on our system. So right now we kind of have the implicit assumption here that every actor is local to us. So every actor is in this map, but we'd like to add logic to say, well, maybe they're not. And I think that maybe requires us to have some idea of maybe when you make this actor system, we connect to some server and we start up the server and the server kind of knows who are all the registered kind of nodes that are interacting with this actor system. So that could be a cool thing we could explore and maybe give us a chance to work with ZIO HTTP and do some stuff there. What happens when it's shut down is all of these fibers that are running these actors are going to be interrupted. So one thing that's kind of helpful to think about when you're thinking about like finalization is like, why do you have the scope in the first place? And so for us, the reason that anything has a scope anywhere is this thing here. This is fork scope, which says we're forking this fiber here that's just processing messages from this queue forever. And fork scoped means when this scope that's forked in is closed, the scope here, then this fiber is going to be interrupted and it's going to stop processing messages. And so now the way we've set it up, if we have this actor system and we create 100 different actors from it, when that actor system is shut down by that scope of the actor system being closed, then all of those fibers are going to get interrupted. And yeah, that's totally right. That right now the logic is we're just going to interrupt them, and we're not going to kind of drain their queue of new messages. We could definitely implement other logic for that if we want. I don't know if it really makes sense to say you would drain the queue, because processing the existing queue, you could easily send more messages to other people's queues. And I mean, I think that just could easily get you in a situation where you're kind of continuing to process messages forever. But you know, you can definitely explore different alternatives there, and that's something that we could do different things for. We could imagine instead that we had some ref we created of whether we were shut down or not, and when the scope was closed, we set that ref, and maybe every time we process, we check and we do something. So there are a bunch of different things we could do there. And yeah, David, so right, exactly. Another kind of right now, we're just going to interrupt this. We could do other variants where we could have that ref that says whether we're shut down. And if we do, maybe then we stop processing the next message, but we kind of don't actually interrupt processing a message while it's in flight. So there are a bunch of different varieties of kind of what shutdown means that we could implement here. And that's just a design decision we could make. And I think pretty easy to implement any of them with ZIO. Yeah, I mean, we can actually do that right now if we want to. So, I mean, a really easy one would be, so let's say shutdown ref and ref.make false. So we'll do let's just fork this as a daemon fiber now. So now keep this scope, but we'll do something else with it. And so we'll do ref.make false. And we have an operator dot with finalizer blank dot set true. Let's see if I can get that. Yep. So again, to kind of my point I made with Juan, this would be kind of think about why you have the scope. So now what the scope represents is when the scope is closed, we're going to set this shutdown ref to true. And so now I think we could, let's see, I think an easy way to do this, I think we could do repeat while ZIO. Just let's see, is that? Let's see if I actually made that up, if that's valid. This is giving us this output, which we don't care about. Okay, so now we're saying, then we still need to fork this. And maybe, let's see, do we like this or? I mean, we could basically invert the logic here, so we don't have to do the negate here if we wanted to. Let's see, just do this thing. Repeat. Okay, so now we're going to take this whole logic and we're just going to do it over and over again until this thing is true. And this thing is going to become true when this finalizer is run. So that's going to give us kind of this behavior of we're going to process the existing in-flight message, but then we won't process the next message. So let's just try and make sure basic example works. And there we go. So yeah, super simple to kind of implement different logic for stuff like this with ZIO. I see you're typing, so I'll. So fork daemon. So fork scoped is the one that introduces the requirement for a scope. Fork daemon basically detaches it from the scope of or not the scope, but the lifetime of whatever fiber this is running on. So even if the fiber that calls make finishes life, this thing will still run until the actor system gets shut down. Generally, I think it's good to think about like you bind your life to like one thing, right? So if we're saying, hey, the whole point of this is that the actor's life is bound to the actor system, then even if I do something like, let's create a silly example here, but here, if I do, if I like fork this whole thing and then this finishes, the life of the actor system the life of the temperature actor should still be bound to the life of the actor system, not to the lifetime of the fiber that created this temperature actor. Okay. Any other questions before we break here? This has been a good session. All right, cool. Well, I will push this code up, and we'll definitely continue this in the future. I'm not sure if we'll have a break next week for something else, but we'll definitely be coming back to this and doing more on this. Yeah, I see Juan's typing, so I'll give Juan one more minute here. Okay. All right. Awesome. Well, have a great weekend, everyone. Take care. Bye.